Okay, so let's talk about stationary distribution of a continuous time Markov chain. In discrete time Markov chain, we have discussed about similar material. Okay. Stationary distribution is actually when you consider a large amount of time, okay, then you can think about the portion of the time you surgeon at a certain state, okay, portion of the time, among whole time you operate the system. Okay. The thing is, when you try to calculate stationary distribution and define stationary distribution in discrete time Markov chain, we consider transition matrix, right? So if you denote stationary distribution of the chain is vector pi, then when we define stationary distribution in discrete time Markov chain, we use two conditions. When you sum all pi i's, there might be 1. And pi i's represent probability, so values might be between 0 and 1. Okay? And second one, when you calculate vector pi times transition matrix P, then you should get pi in discrete time Markov chain. I'm saying about discrete time Markov chain. But continuous Markov chain, we don't use transition probability to define stationary distribution. Rather than using transition probability, we can use generator matrix. Okay, so please don't confuse about two formula how to define stationary distribution of a discrete time Markov chain and the continuous time Markov chain. Okay, so in this case, pi times q equals 0, not just pi or 1 and so on, 0. Okay, sometimes you can be confused of the formula. I'm not going to say why this is true. Okay, why it's true? Because to explain about this connected to the discrete time Markov chain, then we need to solve some differential equations and so on. But I don't want to do that. Anyway, when you try to calculate stationary distribution of the continuous time Markov chain, as long as you can solve a system of linear equation, which includes pi times q equals 0 vector, and summation of all the pi i's equals 1. Okay. Similar to discrete time Markov chain case, you can use invariant measure. When you try first step, you can use invariant measure to solve pi times q equals 0. Okay, and then second step, you can consider summation of all the pi I equals 1. Okay. But when you try to calculate stationary distribution of the chain, before you try to find it, okay, you need to make sure if there exists the unique stationary distribution or not. Okay, as we discussed in discrete time Markov chain, we considered three different words: irreducibility, positive recurrence, and aperiodicity, right? Especially first two words, right? To make sure if there exists the unique stationary distribution of the chain. For continuous time Markov chain, slightly different. When you try to investigate or try to answer the question like, is there unique stationary distribution corresponding to the continuous time Markov chain? Then you need Rodman matrix. Okay. Based on Rodman matrix, you can construct discrete time Markov chain. Okay. You can construct a discrete time Markov chain. We call this embedded discrete time Markov chain corresponding to the continuous time Markov chain you want to analyze. Okay. So slightly confused. Okay. Based on Rodman matrix, we can construct another discrete time Markov chain, and this embedded discrete time Markov chain is irreducible and recurrent. Okay. As long as this embedded chain is irreducible and recurrent, then the original continuous time Markov chain has the unique stationary distribution. I believe you already knew how to figure out whether this discrete time Markov chain is irreducible or not, or recurrent or not, right? But the chain is not the original continuous time Markov chain, but embedded discrete time Markov chain. Okay, let's think about the example. As we discussed in discrete time Markov chain, as long as we can find unique stationary distribution phi I, right? Then we can calculate long run average value, long run average number, long run average time, long run average cost, profit, and so on, corresponding to a function of the chain, a function of the chain. Okay. So we can define long run average measure as limit t goes to infinity. This one, t goes to infinity, 1 over t times integral t is from 0 to large T f of chain x of t dt. Okay, this x of t changes on can change at any point of time, right? In continuous time Markov chain. But when we calculate this one is actually the same as summation for all possible I in the state space. Okay, fi pi I. Okay. So in this example, let's think about. So one of the main topic, main application of this continuous time Markov chain is queuing theory. Okay, when you try to calculate throughput, average waiting time, average number of parts in the factory, and when you try to examine some bottlenecks in the process line, okay, we usually consider this concept queuing theory. Okay, and the measure we can consider the measure long run average number of the parts. Or you can see that, so you can imagine hospital, you want to see the dentist, okay, dental clinic, okay. You can visit the hospital, but every time you visit, you need to wait like 1 hour to 2 hours, okay. Do you want to visit again? 3 hours? No, okay. This is about customer satisfaction. We are going to talk about this later. But the thing is, when you try to operate the system again and again, and the system includes some uncertainty, okay? This hospital system has, when you try to examine how many customer this doctor can handle per day, is about long run average number of customer per day when you operate the system. When you imagine the system, this one is not that easy because arrival times are random. Okay, arrival time of the patients random, and service time. Sometimes a patient want to some easy job on their teeth, okay, or some implant, and so on. These jobs take so long times, okay. We don't know, okay. We don't know which customer will come or not, okay. We can model this using random distribution, okay. So these measures, long run average number, long run average waiting time, and so on, very important measures when you try to examine service system and manufacturing systems. In this example, when you try to operate the system long times, call center, right? We just have 3 lines, 2 identical agents, right? So, if you operate the system long times, how many customers will stay in the system? When you try to connect, what is the probability that connected to the system? Because if this system is full, then we cannot connect, right? Then what is the probability that you cannot connect to the system based on the these probabilities? What do you think? As long as state is 3, then we cannot connect at any point of time. That means with probability 128 over 169, okay, we cannot connect the system, okay. So we can examine the long run average number of customers per unit time using this formula. So we want to calculate, let's say, limit large t goes to infinity, 1 over t, 0 to large t, f of x of t dt. Okay? How can you define function f in this case? Long run average. Per unit time. How can you define the function? F of 0 represent 0 customer. F of 1 represent 1 customer. F of 2 represent 2 customer. F of x is actually x. To calculate the number of averaged number of customers, okay? And then this one is, since the chain has the unique stationary distribution, I is from 0 to 3, f of I, pi I, but f of I is the same as I times pi I. In this case, 0 times 1 over 169 plus 1 times 8 over 169 plus 2 times 32 over 169 plus 3 times 128 over 169. Let's try to calculate it. MATLAB. 1 times 1 over 169 times 1 times 8 plus 2 times 32 plus 3 times 128. The value is 2.69. When you try to connect the system, okay, again and again, okay, then average number of the customer in the system is over 2.6 something. Okay, that means these agents are very, very busy. Okay. and there is a rare chance to connect the system. And then we can calculate the probability. What is the success probability when you try to connect the system? 1 minus 128 over 169.